Hey everyone, and welcome to The Explainer. Today we're going to jump into a really elegant, kind of simple idea that, believe it or not, is the engine behind some of the most complex stuff we use every day.
So let me just start with a question for you. What if most of the data we're constantly juggling, in social media, in scientific models, even in AI, what if most of it is just, empty space? Like just a huge ocean of placeholders.
Okay, so in computer science, we often lay out data in these grids. We call them matrices. And honestly, this is what a ton of them actually look like in the wild. You've got these little islands of real information. See the 9, the 3, the 7. But they're swimming in this vast sea of zeros.
Now you might think a zero is nothing, but to a computer, every single one of those zeros has to be stored. It takes up memory. It takes up processing power. It just slows everything down. The bottom line, it's just incredibly wasteful to store all that nothing.
And yeah, there's a technical term for this. When a matrix is mostly full of zeros like this, we call it a sparse matrix. And trust me, once you start looking, you see them absolutely everywhere.
This isn't some super niche, obscure idea either. It's so fundamental that it shows up right here in the syllabus for a core computer science course on data structures. See? It says right there, students need to learn how to handle a sparse matrix using something called tuple representation.
Okay, so if storing all those zeros is the big problem, what's the solution? Well, this is where things get clever. Computer scientists came up with a really elegant way to handle it, and it's called tuple representation.
The thinking behind it is just beautifully simple. It's like, why are we wasting all this time and energy on the zeros? Why not just only pay attention to the numbers that actually matter? The ones that actually have meaning.
And the process is super straightforward. It's basically 3 steps. First, you just scan the whole grid and find anything that isn't a zero. Then, for each one you find, you just write down 3 little things: what row it's in, what column it's in, and the value itself. That little package of 3 things, that's what we call a tuple. And then the best part, you just throw away all the zeros. Poof, gone. You just ignore them.
When you put these two methods side by side, the difference is just night and day. The old way, the traditional array, is just bloated. It's full of useless information. But this new way, the tuple representation, it's lean, it's efficient. It only keeps the good stuff, the data that actually means something.
And here it is. This is that aha moment. Remember that big, mostly empty 6x6 grid we started with? It's been transformed into this. Just a simple, clean little table. All the important information is still there, right? The value 9 is at row 0, column 3. The value 3 is at row 1, column 1. We haven't lost a thing, except for all the waste.
Let's actually put some numbers on that. The original grid needed us to store 36 different spots. This new tuple format, it only needs 15 entries to hold the exact same info. That's more than a 50% savings. And look, this is a tiny example. Imagine this on a real-world scale. The savings become absolutely astronomical.
So, okay, we've saved space. Big deal, right? Well, yeah, it's a huge deal. And it's all about one thing: making things faster and more efficient.
If we look back at that course syllabus, what's one of the very first things they talk about? Performance analysis, time and space complexity. That's literally the name of the game in computer science. How do we make things faster, and how do we make them use less memory? This whole sparse matrix thing, it's a perfect real-world example of that principle in action.
So you get this huge drop in how much memory you're using, which is great. But it's not just about storage. Think about it. When the computer needs to do some math, it doesn't have to slog through millions of pointless zeros anymore. It can just jump straight to the real data, the numbers that matter. And that makes all the calculations way faster.
And this isn't just theory either. Students are actually put to the test on this. They get lab assignments where they have to do things like, say, find the transpose of a sparse matrix, or add 2 of them together. These are jobs that would be painfully slow if you used the old method. But with tuple representation, they become super fast.
All right, so let's zoom out a bit, because this is way more than just a clever trick for a college class. This whole idea of sparsity is kind of like a secret weapon in some of the coolest tech fields out there today.
Take data science, for instance. Imagine a giant chart with every single customer of a huge online store on one side and every single product they sell on the other. Most people haven't bought most products, right? The grid would be almost entirely empty. The only sane way to manage that kind of data is with a sparse matrix.
Or how about AI? The connections inside a neural network, that's the thing that acts like an artificial brain. Well, a lot of those connections are also sparse. By using this trick, we can build and train way bigger, way more powerful AIs without needing, a giant supercomputer for every little thing.
And here's one you use every day: social networks. Just think about it. Imagine a grid with every single person on the platform. Are you connected to all of them? No way. You're connected to a tiny fraction. That entire network is just one gigantic sparse matrix. It only works because it's super efficient at remembering who is friends and completely ignoring the trillions and trillions of connections that don't exist.
So what's the big takeaway here? It's this. In a world that is just overflowing with data, maybe one of the smartest things we can do is get really, really good at knowing what to ignore. By designing our systems to just step around all the empty space, we unlock the power to work with data on a scale that would have been completely impossible otherwise.
And that kind of leaves us with a final thought to chew on. This whole idea of optimizing for what's not there, of focusing only on what truly matters, it's a massive part of modern computing. It really makes you wonder, doesn't it? What other empty spaces in our digital world are we finding clever new ways to design around? Thanks for joining me.